record this. Okay, so I'm going to record this. I believe that I started recording it. I hope it works. If not, I'll do it again in my own time and post it. All right. So go from the beginning. Oh. Okay, so this is chapter 7 material, and the thing we have to focus on here is, wait a second, I don't think I'm sharing my window, am I? Okay. Okay, good. Okay, that's good. So, so what we want to focus on here are, whoops, sorry, bear with my, you see here the X group, we have an X group here. Be patient with me with the technical problems. I'll get better as we go along. So X corresponds to a halogen. And a halogen is chlorine, bromine, or iodine. Fluorine is also a halogen, but it doesn't really participate in the kind of reactions that we talk about in this chapter. So these are the only ones you have to be concerned about: chlorine, bromine, and iodine. Okay, so in this case, the halogen's attached to an sp3 carbon, and that's referred to as an alkyl halide. And in this structure, the halogen's attached to an sp2 carbon, a double bond. That's part of a benzene ring. That's a benzene ring. That's an aryl halide. And in the third structure, the halogen's attached again to an sp2 double bonded carbon, but it's a double bond of part of a CC double bond. That's called a vinyl halide. Now, in all the reactions in this chapter, the substrates are alkyl halides. So the halogen's attached to a sp3 carbon. The aryl and vinyl undergo these reactions we'll look at, but they're only under special conditions. So you have to make sure that the halogen's attached to an sp3 carbon. Okay. And there are two types of reactions that are the focus of this chapter. One's a substitution, where a nucleophile replaces a leaving group. Okay? So in the product, the nucleophile is now bonded to the carbon, and the leaving group has been displaced. Okay, that's a substitution or a replacement. And then there's a competitive reaction, where a base has a lone pair that can be donated, and a nucleophile has a lone pair that can be donated. The difference is a base forms a bond to a hydrogen. I'm going to show one of the hydrogens on the adjacent carbon. A nucleophile always attacks a carbon, whereas a base forms a bond to a hydrogen. That's the only difference. They both donate a lone pair. Nucleophiles to carbon, bases to hydrogen. And so what happens is the base takes off the hydrogen and the leaving group is kicked out, and you get a double bond between these two carbons. So you end up with an alkene. Okay. An alkene, a double bonded compound. The base picks up the hydrogen, the leaving group's kicked out. That's called an elimination reaction. And in this chapter, we're going to talk about both because they are competitive. So under some conditions, you get substitution, and under other conditions, you get elimination. Okay. So we're going to talk about each in turn and learn about these reactions. So here's a reaction again, substitution. Generic example where Y minus, a nucleophile, replaces X. And here's a specific example. Okay. So let's label the nucleophile and electrophile. So the sulfur has lone pairs. So it's going to donate its electrons. That's the nucleophile. And the chlorine-carbon bond is polar. So carbon is the positive end of a bond dipole. That's the electrophile. Okay. Label the leaving group. So you notice the Cl gets kicked out as chloride ion. So this is Cl is the leaving group. Okay. So whatever gets kicked out is the leaving group. So how does the halogen promote the reaction? Let me show you how that promotes the reaction. So it promotes the reaction in two ways. One we've already reviewed. If you look here, it promotes it by polarizing the bond here and making carbon partially positive. In that way, the nucleophile with a lone pair is attracted to the positive carbon. Okay, there's a place to form a bond. That's one way a halogen promotes the reaction. The other way is that when the halogen leaves, and I'm showing it leaving here, you see this bond is breaking. These electrons are going onto the chlorine. When it leaves, chloride ion is a weak base, right? It's the conjugate base of HCl. And so it's very stable. Weak bases are stable. And so the other way it promotes the reaction is that it can leave very easily. Because it's a weak base, it doesn't bind tightly to the carbon. If the group was a strong base, it would bind tightly and it would have a hard time of leaving. So in general, good leaving groups are weak bases. And we'll see there are other groups that can be leaving groups that aren't halogens. I'm going to show you that in the next slide. So these are a bunch of different leaving groups. These are groups that can be displaced by nucleophiles in a substitution reaction or replaced by nucleophiles. And if you notice in this top group here, these are all strong acids. This is HI, HBr, HCl. This thing here is called a sulfonic acid. Sulfonic acid. Okay. It's similar to sulfuric acid. It's very strong. Notice the pKs are negative. And remember, any acid with a negative pKa is a strong acid, right? So over here, we show the conjugate bases. This, by the way, this is also a strong acid, hydronium ion, -2, right? Everything above this line is a strong acid. It has a negative pKa. And the conjugate bases, they're the ones, that's the base that results when the acid loses H+. So here, HI, the conjugate base is I-, HBr, Br-, HCl, Cl-. This sulfonic acid, you lose a proton here, you get this. This is called a sulfonate ion. Sulfonate ion. Conjugate base of H3O, you lose the H+, you get water, right? So the conjugate bases of strong acids are weak bases, right? So all of these are weak bases because they're the conjugate bases of strong acids, and that makes them really good leaving groups. And a good leaving group is a weak base, right? Everything below this line is the conjugate base of not a strong acid, a weak acid. And so these are bad leaving groups. So when you have these groups attached to a carbon, it's very hard to get them to leave. They stick pretty good to the carbon, right? So in addition to the halogen, we will see other good leaving groups like sulfonate ions and water in future reactions, okay? Okay, guys. So here's an alkyl halide. I want a little more kind of nomenclature kind of stuff. Um, so the carbon that the halogen is attached to is called the alpha carbon. Okay, remember that? And then the carbon next door, that's directly bonded, right? That's called the beta carbon. That's the only two you really have to know. The one the halogen is directly attached to, alpha, and the carbon next door, directly bonded to it, which is the beta, okay? That terminology comes up a lot in this chapter and even in the next chapter. The other thing I want to point out is that alkyl halides are classified in a similar way that carbocations are classified. You look at the alpha carbon, the carbon with the halogen attached. If it has one carbon attached, it's primary. If it has two carbons attached, it's secondary. And if it has three carbons attached, it's tertiary, okay? And that could be, instead of a chlorine, you could have a bromine or an iodine or what have you, okay? So it's the same classification scheme that we saw for carbocations, primary, secondary, and tertiary. So the substitution reactions that I showed you where a nucleophile replaces a leaving group, there's two pathways. There's two ways that can take place, or two mechanisms. I want to show you the two mechanisms. In both of the reactions, two things has to happen, right? The leaving group has to be lost. You lose the leaving group, and the nucleophile forms a bond, right? It involves nucleophilic attack. Nucleophile forms a bond to the carbon, and the leaving group is displaced. But the difference in the two mechanisms is the timing of those processes. So let me show you. In one mechanism, and here's just an example substrate, the first step is loss of a leaving group. See? The bond here is breaking. And you're losing the leaving group, you're forming a carbocation. And then in the second step, the nucleophile forms a bond to the positive carbon, right? Now I have chloride as the nucleophile here. It can be a leaving group, it also can be a nucleophile, but we'll see there's a lot of different nucleophiles that partake in these reactions. That's what makes them so general. So, and that's the final product. The chloride has replaced the bromine. So this process is a two-step reaction, step one and step two, and it's called an SN1 reaction. Okay, so I'll explain the symbolism probably later. Okay, two-step is SN1, and if you want to draw an energy diagram, it would look like this. So you'd have the reactants, and there'd be a barrier to form the carbocation intermediate, right? And that carbocation would react with the nucleophile to give you the product. That's an SN1 reaction. Two steps, two transition states. Okay. The other mechanism, which is more important really, is the one where both processes occur at the same time. So you get nucleophilic attack. Nucleophilic attack. Sorry about that. Well, we'll forget about that. We'll stay more. And then you'll get loss of a leaving group, okay? So you get nucleophilic attack, loss of the leaving group. So they both occur at the same time. Okay, and that mechanism is called SN2, nucleophilic attack, loss of the leaving group. And if you looked at the energy diagram for that, it would look like this. Here's your reactants. Let's say here are your products. That's it. One step reaction. Both processes occur at the same time. And when more than one process occurs at the same time, the reaction is said to be a concerted reaction, right? So like a concert band where you have many different instruments playing together. They're in concert, they're concerted, okay? So I'll explain later why the one-step reaction is SN2 and the two-step reaction is SN1. It relates to the kinetics, but that's how it is, okay? Okay. So we're going to talk now about the SN2 reaction in some detail, and then we'll later pick up on the SN1. Okay, but the SN2 reaction has second-order kinetics. The rate is proportional to the alkyl halide concentration, and it's also proportional to the nucleophile concentration. What does that mean? This is a rate constant, the constant for the reaction under the given set of conditions. It means if you double the alkyl halide concentration, the rate doubles. If you double the nucleophile concentration, the rate doubles. If you double both at the same time, the reaction will go up by 2 times 2 or 4. Okay, so that's a second order reaction. And what that tells you, the rate law tells you the composition of the transition state. So what that rate law is telling you, that's an important thing. So the rate law gives you the composition of the transition state. And so what this rate law is telling you is both the alkyl halide and the nucleophile are involved in the transition state, which is what we saw in the previous slide, right? See, so this one-step reaction, what's taking, the nucleophile's attacking, the leaving group is leaving, and they're both occurring at the same time. So what is the transition state? Here's the energy barrier, one step. What is this transition state going to look like? Let me show you on the next slide. Okay. So there's the reaction here, down here, the energy diagram. Let me explain this. It looks a little complicated. So here's your nucleophile and a substrate. Here's the product where the nucleophile has replaced the leaving group and the leaving group has been kicked out. Okay, so here's your transition state at the top, right? So as you go up this curve, right, the nucleophile is forming a bond to the carbon and the bond to the leaving group is starting to break, right? So up here, and here you go. That's the transition state. The nucleophile here is hydroxide ion, and you see the leaving group is chloride. So at the top of the hill, there's a partial bond to the hydroxide. The dash line indicates a partial bond. And the bond to the leaving group is breaking. The partial bond indicates also a bond that's breaking. Okay. So in the transition state at the top of the hill, the hydroxide is forming a bond and a bond to the chloride is breaking. And as you continue down the curve, more and more bond formation to the hydroxide, more and more bond cleavage to the chloride until you get to the product, okay? You notice in the transition state in SN2 reaction, this is an SN2, right? One step. It's a little crowded up there, isn't it? You have like the 3 atoms or groups that are attached to the central carbon. And then you have the nucleophile and leaving group, which are also partially attached. So it's getting a little congested there, but this is what the general transition state will look like. The nucleophile will change from one reaction to the other. The leaving group will change from one reaction to the other, but the basic structure is going to look like that. Okay. So various nucleophiles and various leaving groups are possible. So here's a list of very common nucleophiles. And we'll see all of these reactions as we study them. What they have in common, of course, is they have one or more lone pairs of electrons that can form a bond to a carbon, right? This is hydroxide. You recognize a bunch of these. Of course, this is water. RO minus is an alkoxide ion. It's the conjugate base of an alcohol. And the most common R groups are methyl, ethyl, that kind of thing. But it could be anything in principle. They're alcohols. This is carboxylate ions. That's the conjugate base of a carboxylic acid. That's a carboxylic acid. And a shorthand way of writing a carboxylic acid is like this, right? That's the condensed version. So a carboxylate ion, if you want to draw it out, would look like this. Okay? It has lone pairs here. It can act as a nucleophile. This is ammonia. And if you replace one or more of the hydrogens of ammonia with carbon groups, you get amines. These are different amines. This is a functional group called an amine. Nitrogen has a lone pair. HS minus is the bisulfite ion. RS minus, where R could be methyl, it could be ethyl, it could be anything. Sorry. Those are called thiolate ions. The negative charge on a triple bonded carbon is called an acetylide ion. Cn minus is cyanide. By the way, the structure of cyanide looks like this. And N3 minus is azide. So all of these are materials that can, nucleophiles that can participate in substitution reactions. And by introducing them, you generate different functional groups. I'm going to show you examples of that. Okay. So let's draw the products. Let's practice. Let's draw the products of these SN2 reactions. All right, and giving you the arrows here, but normally you don't. The arrows won't be included if you're asked to draw a product. So this is a carboxylate ion here, right? Methyl bromide, so you get a nucleophilic attack on the carbon, loss of the leaving group. So the instead of a bromine attached to the methyl, you're going to have the carboxylate ion attached to the methyl. Here it is. Okay. Yeah, now that's attached to the methyl. Right? And this is an ester. And so choosing a carboxylate ion as a nucleophile, you can form esters in this reaction. Here's a bisulfite ion. You're attacking, you always attack the positive carbon. You don't attack these carbons. Why? Well, they're not positive, and they don't have a leaving group attached. You need a weak base attached to the carbon so it can be kicked out. Okay, so be careful. And the atom that's attached to this carbon is the atom with the lone pair, so it's going to be the sulfur. You see now the SH is attached to the propyl group rather than the bromine. Bromine gets kicked out. This is a thiol, functional group thiol. And so using bisulfite ion in these reactions is a way of synthesizing thiols. And finally, we have cyanide, Cn minus. This should go point to that carbon. Iodide is displaced, and so you get the cyanide attached now to the cyclohexene ring rather than the iodide. Notice that the C has a lone pair and the nitrogen has a lone pair, but it's known from experiments that the carbon is the stronger nucleophile. So you'll generally almost always get the bonding to the carbon and not the nitrogen. Okay. So these are all SN2 reactions. This is called a nitrile. And using cyanide as a nucleophile is a way of synthesizing nitriles. Okay. Okay. So let's try a few more of these reactions for practice, and I'll point out no arrows now, and I'm going to point out something else. Now, if you notice, you see these are now given with cations, which is typically, if you do a reaction like this, you find the reagent on the shelf or in the chemical stockroom. It's going to be a sodium or potassium salt of some type. And so what you have to recognize is this is an ionic, these are all ionic compounds. They're composed of sodium. In this one case, it's sodium ion. And this, I'll remind you what that is. That's azide. That's sodium azide. This would be sodium OCH minus. And this would be potassium hydroxide, right? So I think it's easy, once you recognize these are ionic compounds, that the nucleophile here is azide, the nucleophile here is CH3O minus, and the nucleophile here is hydroxide. Okay? So the sodium and potassium, the cations are just spectators, right? They don't really participate in the reaction. And so you're going to get the azide attacks the positive carbon, the leaving group gets kicked out, and you are going to form oops. This is an organic azide, and that's a way of forming azides. In this reaction, the methoxide attacks the positive carbon, bond to the leaving group leaves, and so now you're going to have methoxide attached to the cyclopentane ring. Chloride is going to be kicked out. And this is an ether. This is an example of an ether. And so using these alkoxide ions, or alkoxide ions or RO minus, you can form ethers. And finally, by the way, this structure, I left out a leaving group. Let's put I. Okay. Or the nucleophile hydroxide attaches the positive carbon, the one with the leaving group, the bond breaks. Now the hydroxide is attached. The leaving group gets kicked out. Okay, so this function is an alcohol. So by using hydroxide ion as a nucleophile, you can introduce an alcohol function. So I think you get the idea that this is a very useful reaction in synthetic chemistry. When you're trying to make new molecules, you can introduce a variety of functional groups using these SN2 reactions. Okay. All right, so I have about 10 more minutes left, so I'm going to just, according to my clock, so I'm just going to do this last few slides here, okay? Okay, so this is some data on an SN2 reaction. This is the reaction they studied. You see the leaving group is bromine, and the nucleophile is chlorine, right? Notice that? Leaving group is bromine and the nucleophile is chloride, right? And the reaction is the chloride replaces the bromine and the bromine gets kicked out, so that's an SN2 reaction. And so they studied these different alkyl halides. This is a methyl halide, the bromine is attached to a methyl. This is primary, right? Why? Because the alpha carbon only has one carbon attached. This is also primary. The alpha carbon, the one with the bromine, only has one carbon attached. It's also primary. This one, I hope you see, the alpha carbon has 2 carbons attached, so that's secondary. And this one down here, the alpha carbon has 3 carbons attached. That's tertiary. Okay. So we have a methyl, 2 primaries, a secondary, and tertiary. Look at the rate of the reaction. So they measured how fast these reactions took place. And you see the methyl so they compared them all to the secondary. So they set the rate of the secondary at 1. So these are just relative rates. And you see the methyl halide was 1,200 times faster. The primary halides were also faster. They differed slightly, but they were also faster. And then the tertiaries were too slow to measure. Tertiaries are just slow. They don't undergo SN2 reactions. So from data like this, it was shown that the order of reactivity is methyl substrates are most reactive, then primary, then secondary, and then tertiary. That's the order of reactivity in an SN2 reaction. I'll show you that in the next slide. Okay, relative reactivities of alkyl halides in SN2 reactions. Methyl most reactive, tertiaries least reactive. In fact, they're so unreactive is that they basically don't undergo SN2 reactions, right? So you see methyls, if you look at a methyl, you have very small hydrogens attached, right? I'll put a leaving group on here. Hydrogen's a very small atom, so this is not very crowded around the carbon. You look at a tertiary halide, you have larger R groups around the carbon. This is much more crowded around the carbon. And so these reactions are very sensitive to the size of the groups around the carbon, and I'm going to show you that here. Okay, so let's look at this carefully. So in this slide, you have a methyl bromide and hydroxide, right? And here's the product. OH replaces the bromine. Bromine gets kicked out. And here's the transition state for that reaction, right? Hydroxide is forming a bond to the bromines breaking. Here are the 3 hydrogens of the methyl group. On this, in the energy diagram to the right, you have now a secondary substrate. See that? The alpha carbon has 2 carbons attached and hydroxide. Let me erase this one. Okay. And in the product, you see in the product, the OH has replaced the bromine, right? And the bromine leaving group has been kicked out by hydroxide. And here's a transition state for this reaction. So this is a secondary substrate, right? This was a methyl substrate. So you look at the 2 transition states. In this one, you have five things around the carbon, 3 hydrogens and OH and the Br. And over here, you also have 5 groups around the hydrogen, OH, Br, and then the 2 carbon groups. So these carbon groups are a lot bigger than hydrogens, right? Hydrogens are small, the smallest atom in the periodic table. And here you have a carbon group. It could be methyls, ethyls, it could be bigger group. So what's happening is this is getting really crowded up here. And so the carbon groups start banging into the other groups attached to the carbon. And so this gives rise to what's called steric, remember this term, steric hindrance. Steric hindrance is when groups, the atoms get too close to each other and they start banging into each other. And when they do that, the transition state energy goes up. The strain raises the energy of the species. And so the barrier to the reaction gets bigger. And this is a small barrier, this is a bigger barrier because the transition state is strained. And the bigger the barrier, the slower the reaction, right? So the more groups you have around the alpha carbon, the more strained the transition state's going to be, and the higher the activation barrier, the slower the reaction. So remember, the order of reactivity in SN2 reactions is methyl is greater than primary, is greater than secondary, is much greater than tertiary. Okay. Yeah, I think I'm going to stop there. Okay, I see a few questions. I'm sure. Sorry. Let me respond to these questions. I'll try to be able to view the chat window while I'm giving the talk, so I can respond to them in real time. But let me do that. Can you update the PowerPoint slide? So